Okay, hello everyone. Welcome to today's Introduction to Adams Machinery webinar. So as you all know, we have just released our new Adams 2013.2. We have a few important updates to the existing Adams Machinery capabilities. So in today's webinar, we will be introducing the overall capabilities of Adams Machinery as well as the new updates. So my name is Yichun Fan, and I'm the Product Marketing Manager for Adams. And sitting with me, we have Anthony Gugino. He is the Product Designer for Adams Machinery. And also we have Chris Baker. He is the Product Manager for Adams. So now I'm going to pass the presenter to Chris Baker.
Thanks, Yichun, and thanks to everyone for joining the call today. So to begin, before we talk about the features specifically, I just want to revisit the high-level definition of Adams Machinery, give you a sense of what it is, the sorts of problems it solves, and then I'll hand off to Anthony here, and he'll walk you through some of the specifics regarding the feature content and modules. But again, when it comes to Adams Machinery, really what we've done is we've harnessed the powerful Adams technology that's been around for a number of years, and we've developed a virtual prototyping environment that's much more approachable, easy to use, much more productive for Adams users of all sorts, both proficient and novice. And we'll see through the following slides that, some of the techniques we've implemented to make that the case. So who is it for? As I mentioned, multi-body dynamics analysts. Certainly, the proficient ones even realize quite a bit of value from this from a productivity standpoint, creating very complex systems, including discrete element belts, cables, chains. That process is made much more efficient through machinery. Also, we've realized through surveys and interactions with customers over the course of the past couple years that they're having a hard time identifying and attracting proficient multi-body dynamicists. So what we've done is we've created a tool, again, that's approachable for new users of this sort of technology so that they can take full advantage of the power of Adams. And then likewise, bridging the gap between FE and multi-body dynamics and making the product more approachable certainly helps from a process standpoint. So I've mentioned productivity a number of times. Again, we're providing a high-fidelity simulation that is part of the Adams technology and has always been a nice attribute of the technology. But we've, within the Adams View environment, introduced a wizard-driven set of modules that guide a user through the process of creating components specific to mechanical systems such as gears, bearings, belts, and other components. Right here on the right-hand side, you see one screenshot of the wizard, in particular for the gear pair. And essentially, you can see that, at least from some of this, if you zoom in, you can tell that there's a process by which a user would input parameters and define a gear. And on the left-hand side here, we see that there's a native post-processing environment within Adams as well that allows the user to examine the results. So it's fully integrated post-processing and again leverages that proven Adams solver technology. So the benefits, productivity, we're saving 80 to 90% of time in the model creation process by automating the creation of some of these components and using the wizard environment to do so. We're also making this more approachable, as I mentioned, and by providing higher fidelity simulation with these well-defined components in the way we do, we're giving the user and the user community in general a better understanding of the general behavior of these systems. So some people have asked, well, how is this different from CAD embedded? Others have asked, why are we even comparing to CAD embedded? It's Adams after all. But it's worth talking about because we are talking about machinery products. Well, we've created modeling automation that's very specific to machinery component types, but again, this is Adams. It's not static solution. It's not simply kinematics, but we're looking at dynamics at a very high level of fidelity. And we are shooting, we've developed several solutions that Anthony will discuss in more detail that make this quite differentiated from any sort of cat-embed simulation that you'll come across. Number one, we've introduced the bearing catalog with nonlinear stiffnesses and life estimations. We have a variety of electric motors with varying levels of fidelity depending on the methodology you choose. We have analytical methods and ease of co-simulation with various other 1D tools. And then we also have these custom analytical contact and mass effects that we've coded in there for belt, chain, and cable dynamics. So at a very high level, when we step back and look at this, what do you want to do with machinery? What does the user want to do? And with multi-biodynamic software in general, you're looking to evaluate and tune the dynamic behavior of a system. So we facilitated that by improving the productivity and ease of creation for common mechanical components. So this is really geared towards virtual prototyping of mechanical systems. And you'll see that we have modules for electric motors, gears, belts, chains, bearings, and cables. Methodologies of varying fidelity are available, and various types of each component are available as well. So with that, I am going to hand over to Anthony here to walk you through some of the feature content.
Thanks, Chris. So we'll walk through the feature content here of each of the different modules here, and to piggyback on what Chris has said, this is all embedded in the Adams View environment. So when we talk about Adams machinery and these modules, we're not talking about separate standalone solutions in different environments or anything like that. These are all essentially new modeling elements and tools within the core Adams View environment. I'll start with electric motor module. So this is a brand new module that was just released in our 2013.2 release that came out last week. So brand new module here for modeling electric motors. We bring 3 different modeling options into the product with it. The first is a curve-based modeling option whereby you as a user would be specifying torque versus speed curves, and then the motor would follow those torque versus speed curves, and Adams Machinery Motor would be creating all of the modeling elements required to drive the motor in that sense, state variables and splines and data arrays and things to look up the torque versus speed points that you've applied into the model. The second option is the analytical option. In this case, this modeling method is an equation-based one where the motor torque is based on characteristics of the motor, electric characteristics of the motor, numbers of windings and poles and voltage and current and all these kinds of things. Therefore, this type of modeling method is motor specific. So we've got 4 motor types listed here, a DC and a brushless DC, a stepper motor, and an AC synchronous motor that are represented currently in the software by this analytical method. And then lastly, we've got an external method, which is essentially behind the scenes using the Adams controls package and its style of either external system library import or co-simulation to work with Simulink, EZ5, or FMI compatible models in a co-simulation mode where you've got a very sophisticated representation of the model modeled in an external code. And maybe, oftentimes modeled by folks in other groups at your organization. So what kind of problems are we aiming the electric motor module at? Well, certainly motor sizing is a good problem. The way folks handle motor sizing now is they just put a motion on something and drive it and see what kind of torque that motion has to drive the system. But that can be a good first cut. But to get a little more detailed look at that, you'd like to see how a real actual non-ideal driving actuation happens. How that actually performs with the real torque. And then, you want to have a more accurate torque signature than just a motion or even just maybe some simple torque functions that you may be applying today. the importance of the accuracy of the torque signature is that it allows you to really say, well, what is that motor torque doing to the rest of the system? Is there some oscillation in it that's going to cause and excite a vibration in my system that I don't want? Is it going to have a sufficient oscillation or switch on, switch off motion that is going to, or behavior that's going to cause problem for position control? Am I just going to miss the mark with whatever my precise precision control application is in the rest of my model because the motor torque is coming on too hard or it's vibrating too much itself, causing too many vibrations? So it's really about providing a realistic drive signal so that the rest of the model, the rest of the mechanism, the rest of the machine components, so we can see how the rest of the machine components react to that. The belt module originally offered two styles of modeling these things: a very basic constraint model, just a coupler, and a discretized belt formulation that is fundamentally planar. You use 2D parts or 3D Adams parts, but it's fundamentally planar in terms of the representation of the pulleys and the belts. They're constrained to a plane. And you can see we represent, with those modeling options, we cover smooth, trapezoidal tooth, and poly groove belts. In this release 2013.2, we've added a 3D discretized smooth belt, so that allows non-planar formulation in this case. So it allows offsets and misalignments of those pulleys for things that are either built in by design or that may occur due to compliance in the system during operation. Also this release, we've added a simplified 3D belt. So again, we can have offsets and misalignments of pulleys in this model as well. But this is a simpler model. It's not a fully discretized model. So instead of several massive parts connected by field elements to represent the compliance, this here is really a clever combination of parts and constraints and forces. And it's still very good for representing axial belt compliance, the sliding friction laterally of a pulley along, or the belt along the pulley, of course the belt bending, and changes in span length and the associated overall mass of those spans can change throughout the simulation. So this is a much faster option, really intended for cases when the mass and inertial effects of the belt can be neglected. So you really only need those when you're looking at transverse dynamics, belt, the belt bouncing around in the spans. Other cases, catenary effects, other things where the mass and inertial properties of the belt are significant on the problem you're trying to solve. When it's not, that kind of a model is overkill, and this is going to run much faster. It's very good for, it's really aimed for reciprocating a simple circuit event, so it's not the kind of thing where you want to have this belt, running multiple circuits over and over. And in this release, it currently does not support a pulley liftoff or axial slip, but just the longitudinal slip, or lateral slip, I should say, not longitudinal slip. So overall, people are using the belt module to look at power transmission issues in belt-driven systems, predict the load history, loads in the belt, loads on the pulleys, analyze the impact of the belt slippage, or studying the effects of belt dynamics, particularly with the discretized model. Moving on to the chain module, very similar in structure to the belt module in that we have a constraint mode that's just a kinematic coupler. We've got a planar 2D and 3D links representation for these the roller chain and the involute chain. And then we've also just added this release 2013.2 non-planar behavior for the roller chain so that we can have small roller offsets, sprocket offsets and sprocket misalignments. Somewhat similar to the belt here, with the chain method, the chain model, you'd be looking at addressing or predicting forces in the chain itself to avoid tensile failures of the chain, looking at load histories throughout both the chain and the sprockets and both the sprocket mounts. You'd be looking at analyzing, of course, chain vibration, depending on varying things that are happening, excitations into the system or preloads in the system. and looking at the effect of the chain compliance overall on, again, power transmission and what's happening at the output shaft. With regards to the gear module has two primary modeling fidelity options: a simplified option, which is an analytical contact calculation, and so this is using really resolving the contact between the gear pair down to a single point contact. Typically good for cases where you're mostly in plane. There's some ability to handle some 3D effects, 3D coupling effects of the gear, but a very fast and a very efficient simulation option here. If you really need all 6 degrees of freedom covered, and you can use the 3D contact method. In that case, you can have full 3D contact across the width of the gears, and full range of motion, relative motion between each of the gear pairs, each gear in the pair. And with a 3D contact, we have the ability to represent tip relief on the tooth and crowning for at least for the spur and helical gear types currently. In this release, what we've added is a handful of new gear types: the rack and pinion, the hypoid, and the worm gear. So those are new to the 2013.2 release. Again, just released last week, 2013.2. All three of those support both of those methods I described on the last slide. And in addition, we've done a few other things to the gear module. We've made some overall enhancements to it, allowing folks to make gear pairs out of 2 existing gears that may be paired up with other things. You can imagine a differential where there's a square of beveled gears connected to each other. We also allow mixing methods within a single gear set, like I'm showing in this ABC diagram here, where A and B have a simplified representation, and B and C have a 3D contact representation. There's a few users have requested that. And it was much easier to use input page layout as well. So just how we lay out setting out the gear geometry and defining the gear geometry. There's a lot of inputs to define gear geometry, particularly when you start looking at those modification parameters like the crowning and tip relief. It can be quite a large input set. So that's been improved. Overall, what folks are typically doing with our gear module is they're trying to study the effect of gear backlash on the system performance overall, and predicting the contact force between the gear pairs, as well as that will include looking at the effects of friction. So you can define static and dynamic coefficients of friction, transition velocities in that contact, so that gear friction effects can be looked at. Gear rattle is typically another problem that folks will solve with the Adams Machinery gear module. So really where we draw the boundary is about there. If you have problems that include and really require a look at all aspects of the microgeometry, or that require looking at the flexibility, require representing the flexibility of the gear tooth, deformations, localized stresses and deformations of the gear tooth, Adams Machinery gear is not the tool for you. We've got some other tools to address those kinds of issues, but that's sort of the boundary of where we draw the boundary for what Adams Machinery gear is doing. Moving forward onto the bearing module. Again, you'll notice a recurring theme here, multiple fidelity options here for the bearing module. We've got some very simple methods to represent the bearing as kinematic joints or linear bushings. We've got a detailed method that's very interesting, which allows us to represent, have a detailed model of rolling element bearings here. So 14 different types of rolling element bearings, really families of rolling element bearings within the broader groups of your ball bearing, tapered roller bearings, cylindrical and spherical roller bearings, So sort of the major 5 families or groupings of rolling element bearings. We've got 14 different subtypes of that captured here. From an input standpoint, again, wizard-driven inputs as other things in machinery are. In this case, we have a nice feature in that we have access to a bearing library of 24,000 bearings from 8 different manufacturers to grab off-the-shelf catalog bearings. Inputs are derived in most cases from the catalog. Some of them are come to us directly from the manufacturers for the various input parameters, inner race, outer race radius, number of rollers, roller dimensions, those kinds of things. All those things that are inputs to our calculation. What the calculation here is doing is calculating the force, the nonlinear stiffness, so the nonlinear force response of the bearing to the rest of what the Adams model is trying to do to the shaft that the bearing is holding up. And so this is also providing us a bearing service life at the end of our analysis. We could go ahead and look at service life prediction based on some ISO standards. In fact, the stiffness calculations that are run during the simulation are also based on ISO TS standards. The service life calculation will accept and take into account some basic lubrication and environmental factors like temperature and the lubricant itself, and then it's got a lookup table behind the scenes for viscosities of those lubricants, temperature, and of course load and speed conditions will also drive that life prediction. So moving on, what problems does it solve? Looking for this bearing module, we're primarily looking at, you can do a couple of things with it. People are looking at changing the effect of the bearing parameters, seeing the effects of changing the bearing parameters. So you may change the clearance of the bearing, you may be changing the, in addition to changing the clearance of the bearing, you may be looking at changing bearing sizes, trying to see what happens when you have different size bearings at different places in the system, and of course predicting loads in the bearings, in addition to seeing what clearances in the bearings may do to the rest of the system. You also may be interested in knowing what kind of loads and getting accurate load prediction, having an accurate stiffness response with the bearings to know what the actual loads are going to be going into those bearings, so that you can find the trouble spots in any bearings within the and compare all the bearings in the system, and again adjust sizes and things from there as needed. Lastly, I'll talk about the cable module here in Adams Machinery. The cable module, again, similar to the belt and the chain modules, has a simplified, some simplified methods and some discretized methods, more similar to the what I described in the belt method. In fact, we've got a massless method where the mass and inertias of the cable are neglected, and it's just a force-based representation of those cables. It's very, very fast and very good for cases when, again, the transverse dynamics of the cable are unimportant to you. And then there's the discretized method, which does, of course, take into account the mass properties, the mass and inertial effects of the cable along the spans, and can do a very, very nice job of predicting cable vibrations. So here, similar to what maybe folks will be looking at in the belt module, you're trying to look at the tension within the cable at all the different spans and making sure that it's not overloaded, looking at the load histories on the pulleys themselves, assessing the effects of cable dynamics on your system. In the case of that discretized model there, there's going to be undesired vibrations on that cable. The module does support out-of-plane motions during the simulation of all the pulleys. It also supports some basic winching effects whereby you can release more cable into the system or draw in cable during the analysis. So a wide variety of cable issues can be solved with this module. Lastly, I'm going to touch on a few general enhancements that we've made in the 2013.2 release. Overall to Adams Machinery, general enhancements here. We've expanded the parametric modeling capabilities, so things like belts and chains can rewrap automatically when you're moving things like pulleys around or changing pulley diameters around. There are more properties in general exposed for the various parametric study tools within the Adams product family. There are some improvements made to the dependency handling as well. What we mean here is it's just more flexibility involved with the ability to copy, modify, and delete some of these higher order objects. Kind of reduce some of the trade-offs we've had with having a nice big nice big single higher order object here that can be modified as itself. Now we've got some capabilities where you can modify some of the key subcomponents of that individually, and some ease of use in modifying the models, particularly with some enhanced wizard navigation that's going on. Also done some visualization improvements on the pulleys and sprockets, abilities to more easily tell which pulley and which sprocket is what in your big old system of these things. If you've got 10, 12, 20 of these things, and some nice options for graphically picking those while wrapping cables and belts and chains and these things. And lastly, we've improved the wizard file. So the wizard file format has been improved. This is the thing that allows you to save the content of everything you've entered on 4 or 5 pages of wizard entries to build up one of these subsystems, and this file has been improved to be much more name value paired. It's a very simple XML file format, so it's a little more easy to read. And we will continue to support the earlier formats as well, the earlier format from previous versions that was out there moving forward. Okay. So with that, I will turn it over to Yijin, who's going to show a few examples of some real specific engineering problems that have been solved with Adams machinery. So, okay, go ahead, Yijin.
Thank you, Anthony. Okay, having reviewed the detailed functionalities of Adams machinery, let's take a look at how the product can be used to solve some real-world problems. So the graphic here shows a typical Serpentine belt system layout. And the drive is on this pulley, and the belt wraps around a series of idlers and also other pulleys and ends where it started. So the input function of this drive pulley can be defined in any way the user wants. For example, you can simulate that as an internal combustion engine or an electric motor. Likewise, we can also define what is being driven in the system. So the focus here in this case study is at this particular pulley. So we add a drag torque on this pulley so that in the beginning, when the whole system belt starts to move, this pulley keeps still. And what we try to do is that we're trying to change the angle of this tensioner pulley so that when the system loading reaches a critical point, this pulley starts to pick up and rotate. If you can take a look on the plotting on the right hand side, as throughout the whole analysis, the loading, the tensioner torque is increasing gradually, and when it reaches certain point, the angular velocity of the pulley in the white circle starts to show up. So it increases from 0 to a certain value of about minus 225 degrees per second, which means this is the critical point where there's a sufficient load to drive the whole system. And with the further increase of the tensioner torque, we can see that the angular velocity doesn't change. So everything on the right-hand side of this critical point, from the perspective of the tensioner torque, it's excessive torque. So to sum up, from this case study, we can say that the minimum necessary tensioner load is identified. And also we can match the belt specification to the usage environment. And also, last but not least, because we can figure out the critical point of this tensioner loading condition, we are able to design and optimize the whole system without the parasitic loss or low efficiency. So we're not over-engineering anything. We're just trying to figure out the optimum value to drive the whole system. And the second case study is we are having a chain dynamic correlation case study here. So this case study comes from a customer which is a supplier to a major auto OEM. So they were building those chain tensioner to the chain system that was used in the vehicle. And in this case, the problem is that when they're performing the physical test on their tensioner and chain system, they have identified a chain flutter issue around here. So the local frequency of this chain system actually are interacting with the whole system frequency, which causes the resonance effect and a lot of vibration and noises. So what we did in this case study is that we are trying to reproduce the system using Adams and Adams machinery. So we studied the sensitivity of various parameters until we had a well-correlated virtual model to the physical test results. So let's take a look at some of the results. So as it's shown on the plot on the right-hand side, the physical test is available here on the dotted lines. So there are two conditions that we are particularly interested in, that is with the pretension off and pretension on. So with the pretension off, we can see that the resonance, this is the yellow dotted line. So this is the physical test results. So with the pretension off, the whole system reaches its resonance frequency at about 175 Hertz. And but when we turn on the pretension, the system resonance frequency have shifted to about 250 Hertz, and also the amplitude has also increased. So with a after we performed all the sensitivity study using Adams and also Adams machinery, we are able to figure out a simulation result that correlates very well with the testing results. So as it's shown here on the graph, we have this frequency domain drive motion torque results with the pretension off and pretension on. Those are the Adams simulation results. So with the pretension off, we can see the red curve represents the frequency domain analysis of the drive motion torque, and that is actually matching very well with the test results. And also when we are turning on the pretension, we can see there that from the blue curve, it also correlates with the physical test results very well. So with that kind of matching and with that high fidelity model, we are very confident that we can, from this point forward, we can go ahead and study, fine-tune the system so that we can diminish the resonance effect. So several benefits gained from this case study is that first, we have a working model that correlates to the test results successfully. And secondly, we will be able to shift the resonance frequency to an accepted value. And actually, that's what happened in that company after this, after they have using Adams machinery. And also, we are able to stay within the prescribed system constraints. So not engineering a solution which actually we don't make in the real life. So this is the second case study. And the third case study we performed is about the Geartrain rattle prediction, in which we predict whether the gear rattle will be a concern under representative load conditions. So this is a industrial Geartrain model built up within Adams. And also, we made this input shaft flexible using the Adams reflex functionality. And all the rest of the components, like the bearing and also the gear, they are built up using Adams machinery. So we're studying the interaction between two gears, the driving gear and the driven gear. The driving gear is this green gear, and the driven gear is the red gear. So we're trying to simulate the rattling effect of this driven gear with the input function defined at this input shaft. And also we have identified the damping coefficient and also damping coefficient of the and the inertia of the driven gear here. So if you take a closer look at this animation, you can see that there are rear and front contact between the driven gear and the driving gear. as if you can take a closer look. So rear, front, and then rear, and then front. Also, if you take a look at the plotting on the right-hand side, we can show that there are contact forces appearing at exact same moment where there's geometry contact between the two gears. And also that contact force is changing side depending on the real 3D geometry situation. And so we were able to actually perform the simulation of about 0.5 seconds with 300 steps, and it takes about 15 to 20 minutes for a 2-year-old laptop to solve the whole to run the whole analysis. So some of the benefits, obviously, we can we can observe the double-sided contact between two gears. And also we are able to use the model to identify the influential system parameters. And last but not least, from this point on, we are confident that we can use this model to also tune the system to achieve the desired rattle-free behavior. And it goes without saying that using this kind of high-fidelity model, we can use that to design away from the problem. So when we are investing in the really expensive hardware and physical tests, we have full confidence that the system is going to work in the way that we want it. So we hope that as a result of the presentation, you've gained an appreciation as to how Adams machinery can assist in these areas. And of course, the real proof of any tool is that what value it can bring to your own process. So if you want us to schedule a demonstration, or if you want us to see how Adams machinery can help with your product or design process, please do contact this, send an email to me, and we will have our application engineer help you observe your design environment and see how Adams machinery can help you build a better product. So with that, I will end the presentation, and let's go to the Q&A session.